Now let's look at the independent samples t-test. When would we use an independent samples t-test? Now basically when we've got two sets of samples, if you will, that are independent from one another, and we want to see if there's a difference between those two groups. Some classic examples are we're looking at a drug versus placebo type of study. If we're looking at antidepressant compared to a placebo, and to see if it does better than a placebo in the research. So we've got two groups. We'd have subjects that were randomly assigned to one of the two groups, and we're looking to see if there's differences between the two. Gender differences research or sex difference research, that would be another example of looking at boys versus girls on various things as reading, the differences in which there are been consistent significant differences of girls performing much better and significantly higher in reading as compared to boys. Conversely, for math, there's no sex differences. Now those have been pretty much wiped out. So we also, they can be called independent measures or between subjects designs. And then here's one way in which we could write out our hypotheses for this. Now, the structure of this is the same as what we've had before. We're just looking at the observed mean difference divided by the difference we'd expect by chance, or our estimated standard error. And so it's going to be the sample mean for one minus the other sample mean divided by this estimated standard error. Getting at that estimated standard error is a little bit more work for this. So one of the things that we're going to need to get, if there are different sample sizes in the two groups, we're going to have to get what's called a pooled variance. You see the symbol for this, S sub p squared. The pooled variance is just a weighted average variance. One formula to be able to get this, probably the easier formula to work with, we get the sum of squares for the first group, and we add that to the sum of squares for the second group. And then the degrees of freedom for the first group plus the degrees of freedom for the second group. Notice how this is set up, a line going across, so we add across first, add across, then we'll divide. Once we have that, then we want to get our standard error, the mean difference. Okay. Once we have the pooled variance, then we have that pooled variance divided by the sample for the first group, and then that same pooled variance divided by the sample for the second group. You'll notice here, instead of here where this line went across, here we divide first, then we add them together, and then we'll get the square root of that. Okay? The degrees of freedom, we get the degrees of freedom for the first group, and we figure out the degrees of freedom for the second group, and we add those two together, and that's our degrees of freedom for this. Let's work through a problem. So if we want to look at the impact of infant massage on weight gain for premature babies, and so we have babies who are randomly assigned to a group to get specific systematic massage. The other group doesn't get. The other group of premature babies does not get this massage. And you see we've got our means for the amount of weight gain that's taking place. We've got our variances for each and our sample sizes for each. Our hypothesis, null hypothesis, the mean for the first group minus the mean for the second group equals 0. Alternative is the mean for the massage group, and the mean for the no massage group does not equal 0. Again, equals versus does not equal, we're looking at a two-tailed test. We'll stay with the standard alpha of 0.05 two-tailed test. Now as we look this up in the back of the book, you remember what we need are degrees of freedom. So the degrees of freedom for here, for the massage group, is 15, right? 16 minus 1. Degrees of freedom for the no massage group, 22 minus 1 will give us 21. Okay? So our total degrees of freedom for those two, we add them together, would be 36. So we're going to look this up in the back of the book. And here's our t-distribution. We're in proportion two tails combined, so we're in this column here. and we're going down for the degrees of freedom, and we're looking for 36 for our degrees of freedom. You'll notice over here, if you can see it, there's 30 and there's 40. There's no 36. Now, your natural inclination is to say we'll use 40, but statisticians are inherently conservative, and so they're going to choose 30 because that makes it a more stringent standard for which to make a comparison. And so we go across here, two tails combined, 0.05, 2.042. 2.042 is our cutoff value for this. And since it's two-tail, negative 2.042. Okay, we've got our critical regions. We have our hypotheses. We want to go through and do our calculations now for this. So remember the formula for the t-test. We're just looking at mean differences between the two groups divided by the estimated standard error of the mean difference. It's the pooled variance divided by the sample size. And to get our pooled variance, and remember, we only want a pooled variance when our sample sizes are different from one another. That way we want to get a weighted mean difference, a pooled variance, excuse me. And so when we're working on this pooled variance, the formula for that, one of the formulas to use, I think is the easier one to use. Our sum of squares, we add those together. Degrees of freedom for the two groups, we add those together, and then we'll divide. Okay. So one of the things you'll notice up here, though, is we do not have, we don't have the sum of squares. We have the variances, we have our sample sizes, we have degrees of freedom, but we don't have the sum of squares. If you remember the formula for a variance, it's just the sum of squares divided by degrees of freedom. So if we work that out, if we want to figure out instead what the sum of squares would equal the variance times degrees of freedom. So if we do that for this first one up here, our sum of squares would just be 4.3 times degrees of freedom of 15, 64.5, and 4.9 times 21 give us 102.9. Okay, so we've got that. For your homework, I think you're just going to be given the sum of squares, so you won't even have to do that extra work. That's just bonus for you here. All right, let's go through this. And the first thing I think would be easiest for us to do is to figure out what this pooled variance is. So we've got 64.5 plus 102.9 divided by 15 plus 21. So 64.5 plus 102.9 divided by 36, 4.65 is our pooled variance. If you look at this, that 4.65, that seems to fit, right? It's a mean, it's a weighted mean between these two. And it should be more heavily weighted towards the 4.9, which it is. So we've got our pooled variance. Here's our formula. We've got everything that we need for this formula now for the t-test. We've got our mean difference, so we can do 7.3 minus 5.8. That will give us our mean difference, divided by, and then we want to figure out what's the difference we'd expect by chance between these two groups. Our pooled variance is 4.65 divided by the sample size, 16. Notice that it's a sample size here now, not the degrees of freedom. That's where a lot of students will make a mistake on their homework. and then divide by this sample size, which is 22. 4.65 divided by 16 is 0.29 plus 4.65 divided by 22, 0.21. We add those together, we get 0.5, and 0.5, the square root, 0.71 with rounding. Okay, so that's our mean difference here is 1.5. That was easy for us to get. Here's the difference we'd expect by chance, 0.71, that took us a while to figure out. 1.5 divided by 0.71, t equals 2.11. 2.11, we look at that here, barely in our critical region, but it is in our critical region. Again, we'd reject the null hypothesis here. And then when we look and interpret the results, we look back up at our means and we say the infant massage seemed to work in terms of helping with weight gain for these premature babies.